Hi, I'm Grace Fan, and I'm co-presenting with Amod Katiwada on our work called SANTOS, Relationship-Based Semantic Table Union Search. This is a work done at Northeastern University with Roei Shraga, Zishuan Chen, Professor Wolfgang Gatterbauer, Professor Renee Miller, and Professor Mirek Reidewald. Suppose a data scientist wants to find a table that is related to their table about parks. For example, it can include information on the park name, the supervisor of the park, and the city and country that the park is in. And they want to find relevant tables from a data lake or a centralized repository that is designed to store and process large amounts of data. One option they have is that they can search for relevant tables using the column names of their query table. However, oftentimes the metadata of data lake tables or the column names are unreliable, inconsistent, missing, and generally poorly managed. And keyword search or search over data or metadata often misses a lot of relevant tables from the data lake and has false negatives, or may very well return an overwhelming number of irrelevant tables or have false positives. This leads to the problem of data-driven table discovery, in which given a query table Q, we want to find the top K tables from a data lake that are relevant to table Q. And let's refine the problem of finding relevant tables to finding joinable tables and unionable tables to a query table. In joinable table search, the return tables can be joined with query table Q such that it can augment Q with additional attributes. And in unionable table search, the return tables can extend query table Q with new tuples. We focus on the problem of unionable table search in our work titled SANTOS, Relationship-Based Semantic Table Union Search.
Today we present a new table discovery system called SANTOS, which is a relationship-based semantic table union source technique. Given a query table by the user, whom we consider to be a data scientist, SANTOS returns the top K data lake tables that can be unioned with the query table. Here, K is the positive integer given by the user, which is the number of data lake tables that user wants SANTOS to return. To make the use case concrete, let's assume that we have a data scientist who is collecting information about different parks for certain analysis. Let's assume that the data scientist already has a query table as shown in table A, which contains information about the park like park name, supervisor of the park, the city in which park is located, and the country of the park. Let's consider that the data scientist wants to add more rows to this table. That is, they are looking for the unionable tables. Also assume that we have table B and table C in the data lake, which are the candidate unionable tables. Here, table B is about the movies shown in different parks, and table C is about the people, their occupation, birthplace, birth country, and the parks in which they were seen before. Note that we show the metadata like column headers for the understanding purpose, but they are generally inconsistent and imprecise in real scenario. For example, we have city as a column header in table A, but park city in table B, although both describes the city where the parks are located. Now there are existing techniques that performs the table union source over the data lakes. They generally look for the number of unionable columns with better match between the query table and the candidate tables. For example, table B has two unionable attributes with table A. Here, park name can be unioned with park name and city can be unioned with park city. Similarly, table C has four unionable attributes with the query table. Supervisor can be unioned with person, city can be unioned with birthplace, country can be unioned with country, and park name can be unioned with park name. So, if we use the existing techniques to perform the union source, then table C is considered as the better match because it has more unionable attributes than table B. Notice, however, table C is not primarily about the parks. And if we union table C with table A, then we face a problem of false positive unioning and add erroneous tuples to the query table. For example, we added a tuple that mentions that Central Park is located in Boston, which is not correct. Hence, we argue that the column semantics are not enough to infer the table unionability. On what follows, we also propose SANTOS, which, along with the column semantics, also considers the binary relationships between the column pairs. For example, in table A, park name has a binary relationship with supervisor and another binary relationship with city. Note that for conciseness, we have superimposed the binary relationships in table B and table C. So to summarize our contributions, we present SANTOS, a new table union source technique that uses both column semantics and binary relationship between the column pairs to infer table unionability. In SANTOS, we make a use of external knowledge base and create a data-driven synthesized knowledge base to infer column semantics and relationship semantics. Now we will present the building block of SANTOS in high level. As we want to make the use of column semantics as well as the relationship between the column pairs, we represent each table in the form of semantic graph, where the nodes represents the columns and edges represents the binary relationship between the columns. For example, the semantic graph for table A and table C are shown in figure B and figure D respectively. By using the semantic graph, we can consider both column semantics and the binary relationship between the columns. To annotate the nodes and edges of these semantic graphs, we make a use of an external knowledge base. In our experiments, we use Yago, but SANTOS can be implemented using any other general or domain-specific knowledge bases. We annotate the nodes with the types and edges with the relationship between the entities in the knowledge base. We also assign each node and edges with a confidence score. Please visit our paper for more technical and implementation details. However, one famous problem of using the knowledge bases is their limited coverage over the entities in the data lakes. Hence, relying solely on one or even a set of knowledge bases may not be effective. Therefore, in SANTOS, we also propose a data-driven synthesized knowledge base that is created by using the values in the data lake itself. Specifically, we assign dummy column semantics and dummy relationship semantics for the columns and column pairs in the data lake tables, even if we do not know their names. While assigning a synthesized column semantics, we make a couple of assumptions. First, we assume that the values in the same column are of same type. For example, since Branch Park and Kills Park are in the same column, we assume that they have the same type, although we do not know their type. Furthermore, we also assume that if two columns have overlapping values, they probably have the same type. For example, since column A and column D of table 1 and table 2 have two overlapping values, highlighted on blue, we assume that column A and column D probably have the same column semantics. Now, based on these concepts, we assign the synthesized column semantics along with a confidence score, which indicates how confident we are on the assigned dummy type. We follow the similar concept while assigning the synthesized relationship semantics and assume that the column pairs in a functional relationship have a possible relationship, even if we do not know what the relationship is. Also, we assume that if two column pairs have overlapping value pairs, they possibly have the same relationship. Based on these assumptions, we assign synthesized relationship semantics and assign a confidence score to each relationship. Until now, we discussed how we create semantic graphs based on external knowledge base and synthesized knowledge base. Now we will briefly explain overall pipeline of SANTOS. SANTOS has two phases. The first one is offline phase, which comes before the user provides a query table. In this phase, we create semantic graphs for the data lake tables and index them. During creation, we first try to use the external knowledge base to find column semantics and relationship semantics. However, if we cannot find them, then we use synthesized knowledge base. In the query phase, the data scientist provides a query table, and we first find its column semantics and relationship semantics using external knowledge base as well as the synthesized knowledge base. Then we retrieve the index created in the offline phase to find the top k unionable tables. Please find more details on our paper.
Now that we have the methodology of SANTOS, we continue with our experiments in which we want to answer three major questions. First, we want to see how important is it to use the relationship semantics of tables rather than just using the column semantics like in previous works. Next, we want to see how important are each of SANTOS's components when searching for the top k tables. Specifically, we want to see how important it is to use an external knowledge base and a data-driven synthesized knowledge base to find the semantics of tables. And lastly, we want to see how scalable is SANTOS in searching for these tables in the context of data lakes. Next, we describe our setup. For our benchmarks, we use an existing benchmark from Table Union Search, which we call TUS. In this benchmark, there are 1,500 tables that have been derived from 10 tables from Canada Open Data. We have also created two new benchmarks, which we call SANTOS Small and SANTOS Large benchmarks. In the SANTOS Small benchmark, there are 550 tables that have been derived from 300 tables from Canada, UK, US, and Australia Open Data. We have manually labeled the ground truth for each of these query tables, and this benchmark is mainly used for effectiveness results. And for a SANTOS Large benchmark, there are 11,000 tables that all come from Canada and UK Open Data. Both of these new benchmarks are available openly. And for our baselines, we have D3L, a column-based approach that finds related tables based on 5 metrics: column names, value overlap, formatting, word embeddings, and domain distributions. Next, we have TURL as a baseline, which performs representation learning over web tables for tasks like column type annotation and relation extraction. For our effectiveness, we find that SANTOS outperforms the state-of-the-art method, the column-based approach D3L, by 25% in mean average precision on the existing TUS benchmark, by 78% on the SANTOS small benchmark, and 165% on SANTOS large. This shows that relationship semantics are needed in addition to column semantics. Next, we perform an ablation study in which we tune the coverage of table semantics found using an external knowledge base. We find that the best result comes from using both knowledge bases shown by SANTOS full in the graph. They have a mean average precision of 80% on TUS benchmark and 93% on the SANTOS small benchmark. This shows that the synthesized knowledge base, which represents relationship semantics that may not be contained in an available knowledge base, improves mean average precision by 8% on the TUS benchmark and by 43% on the SANTOS small benchmark. Thus, both knowledge bases are needed for SANTOS. And in efficiency experiments, we find that SANTOS's query time on SANTOS large benchmark is around 5 times faster than the state-of-the-art method. And so SANTOS does scale well in the context of data lakes. In conclusion, we have presented SANTOS, a new technique for table union search that leverages semantics of not only columns, but also binary relationships between columns. SANTOS uses both an external knowledge base and a novel data-driven synthesized knowledge base to find these column and relationship semantics. In experiments, we see that SANTOS outperforms the state-of-the-art table union search method on all benchmarks. We have also openly provided the new SANTOS small and SANTOS large benchmarks. Thank you.